All right, today we're going to pull back the curtain on a core tool in electrical engineering, the phasor diagram. It's really the key to actually seeing that complex dance between voltage and current in AC circuits. So let's jump right in.
Electro knowledge. Power up your concepts.
First up, let's do a quick comparison. You know, in the straightforward world of DC circuits, we have resistance. Nice and simple. But in AC circuits, the opposition to current is a whole different beast. We call it impedance, and we label it Z. And here's the key. It's a complex value. That just means it has both a size, a magnitude, and a timing component, which we call a phase angle. And believe me, in AC, that timing is everything.
And that brings us right to the heart of the matter in AC circuits. This whole problem of phase. It's all about the timing.
See, in an AC circuit, the voltage and the current, they don't always move in perfect lockstep. There's often a tiny time delay between their peaks and valleys. And that time difference, that's what we call the phase shift. It's this supercritical but totally invisible relationship. And to see it, well, we're going to need a special tool.
And that special tool, you guessed it, is the phasor. The best way to think about it is like an engineer's map for navigating the pretty complex world of these AC phase relationships.
So what exactly is a phasor? Well, the textbook definition says it's a complex number. But what it really does is cleverly pack two essential pieces of information about a sine wave, like our AC voltage or current, into one simple, elegant visual. Honestly, the easiest way to picture a phasor is to think of it like an arrow, a vector. The length of that arrow tells you its magnitude, how much voltage or current you've got. And the angle it's pointing at, that represents the phase, that timing difference we've been talking about. So you get magnitude and timing all wrapped up in one tidy package.
And here is why this is such a game changer. By turning these wavy, complicated, time-varying signals into simple little arrows, phasors let us ditch the complex calculus and instead use basic algebra to solve our circuit problems. That's not just a small simplification, that's a huge deal.
Okay, enough theory. Let's see how this all works in practice. We'll start with the simplest, most well-behaved component in any circuit, the good old resistor.
In a circuit with only a resistor, there's absolutely no drama. The voltage waveform and the current waveform rise and fall at the exact same time. They are perfectly synchronized, or as we like to say in engineering, they are in phase.
So, what does this mean? It means the phase shift between the voltage and current is 0 degrees. The impedance of a perfect resistor has a phase angle of 0. This is our baseline, our reference point. Everything else is measured against this.
Now, let's bring in the two components that really stir things up, inductors and capacitors. Their opposition to current is called reactance, and you'll see pretty quickly that they behave as perfect opposites.
Let's just break down their differences right here. An inductor's reactance, it comes from a magnetic field, and its opposition actually goes up as the frequency increases. A capacitor's reactance comes from an electric field, and it does the exact opposite. It goes down as frequency increases. And here's the most important part for us today. In an inductor, the current lags behind the voltage. But in a capacitor, the current actually leads the voltage.
Let's dig into that for a second. Inductors, by their very nature, fight against any change in current. By storing energy in a magnetic field, they essentially act like a heavy flywheel, making the current slow to respond. This is what causes it to fall behind the voltage that's trying to push it. So, for a perfect, ideal inductor, the voltage is ahead of the current by exactly 90 degrees. This means its impedance phase angle is a positive 90 degrees.
And capacitors, well, you guessed it, they do the exact opposite. They resist changes in voltage by storing energy in an electric field. This lets the current rush in and start building up before the voltage across the capacitor has even hit its peak. That's why we say the current gets ahead or leads the voltage.
And for a perfect capacitor, this means the current leads the voltage by 90 degrees. So we represent this with an impedance phase angle of negative 90 degrees.
Okay, so let's do a quick recap. We've got resistance sitting at 0 degrees, we have inductive reactance pointing up to plus 90, and capacitive reactance pointing down to negative 90. How do we combine all these opposing forces? Well, that's where the beautiful and simple impedance triangle comes in.
Building this triangle is actually really straightforward. First, you draw the resistance, R, flat along the horizontal axis.
Then, since the inductive and capacitive reactances are in a constant tug of war, we just find the net reactance by subtracting one from the other, and we draw that on the vertical axis. The hypotenuse of the triangle that connects those two sides, that gives us our total impedance Z.
And this is where we see the real power of thinking geometrically. From this one simple triangle, basic high school trig gives us everything we need for a series RLC circuit. We can calculate the total impedance magnitude using Pythagoras' theorem, we can find the overall phase angle, and we can even apply a new version of Ohm's law made just for AC circuits.
So at the end of the day, the impedance triangle isn't just some neat little trick. It's a really comprehensive tool. It gives us a complete visual and mathematical picture of the total opposition to current, taking into account both the simple resistance and those competing effects from the inductors and capacitors.
And that brings us to a final, pretty interesting question. We've seen that inductive and capacitive reactances are opposing forces, right? One points up, one points down. So, what happens if we could find a frequency where they are perfectly equal, where they cancel each other out completely? What could engineers do with a circuit that, at one very specific frequency, suddenly behaves as if it were purely resistive? Well, that perfect balance, it's a concept called resonance, and it's the key to just about everything from tuning a radio to designing complex filters. But that's a story for our next explainer.
Thanks for watching. Like, share, and subscribe to Electro Knowledge for more electrical concepts.